My name is Mumshad Manambat, and we are going through the Certified Kubernetes Administrators course. In this section, we look at various concepts related to scheduling in Kubernetes. We saw how to install and configure a scheduler briefly in the previous section. Here, we take a closer look at the various options available for customizing and configuring the way the scheduler behaves through a set of fun and challenging practice exercises. Now, I'm going to rearrange the topics a little bit to improve the flow. We will start with manual scheduling and see how you can schedule a pod manually. We then look at daemon sets, labels and selectors, how resource requests and limits play a role in scheduling. We also see how to configure multiple schedulers and how to view the scheduler events. Well, let's get started, and I hope you enjoy the lectures and practice tests. Okay, in this video, we're going to walk over the practice test on manual scheduling. So the question is, a pod Hello and welcome to this lecture on labels and selectors. My name is Mumshad Manambat. What do we know about labels and selectors already? Labels and selectors are a standard method to group things together. Say you have a set of different species. A user wants to be able to filter them based on different criteria, such as based on their class or kind, if they are domestic or wild, or say by their color. And not just group, you want to be able to filter them based on a criteria, such as all green animals, or with multiple criteria, such as everything green that is also a bird. Whatever that classification may be, you need the ability to group things together and filter them based on your needs. And the best way to do that is with labels. Labels are properties attached to each item, so you add properties to each item for their class, kind, and color. Selectors help you filter these items. For example, when you say class equals mammal, we get a list of mammals, and when you say color equals green, we get the green mammals. We see labels and selectors used everywhere, such as the keywords you tag to YouTube videos or blogs that help users filter and find the right content. We see labels added to items in an online store that help you add different kinds of filters to view your products. So how are labels and selectors used in Kubernetes? We have created a lot of different types of objects in Kubernetes: pods, services, replica sets, deployments, etc. For Kubernetes, all of these are different objects. Over time, you may end up having hundreds or thousands of these objects in your cluster. Then you will need a way to filter and view different objects by different categories, such as to group objects by their type, or view objects by application, or by their functionality. Whatever it may be, you can group and select objects using labels and selectors. For each object, attach labels as per your needs, like app, function, etc. Then, while selecting, specify a condition to filter specific objects. For example, app equals app1. So how exactly do you specify labels in Kubernetes? In a pod definition file, under metadata, create a section called labels. Under that, add the labels in a key value format like this. You can add as many labels as you like. Once the pod is created, to select the pod with the labels, use the kubectl getPods command along with the selector option and specify the condition like app equals app1. Now this is one use case of labels and selectors. Kubernetes objects use labels and selectors internally to connect different objects together, For example, to create a replica set consisting of 3 different pods, we first label the pod definition and use selector in a replica set to group the pods. In a replica set definition file, you will see labels defined in 2 places. Note that this is an area where beginners tend to make a mistake. The labels defined under the templates section are the labels configured on the pods. The labels you see at the top are the labels of the replica set itself. We're not really concerned about the labels of the replica set for now, because we're trying to get the replica set to discover the pods. The labels on the replica set will be used if you were to configure some other object to discover the replica set. In order to connect the replica set to the pods, we configure the selector field under the replica set specification to match the labels defined on the pod. A single label will do if it matches correctly. However, if you feel there could be other pods with the same label, but with a different function, then you could specify both the labels to ensure that the right pods are discovered by the replica set. On creation, if the labels match, the replica set is created successfully. It works the same for other objects like a service. When a service is created, it uses the selector defined in the service definition file to match the labels set on the pods in the replica set definition file. Finally, let's look at annotations. While labels and selectors are used to group and select objects, annotations are used to record other details for informatory purpose. For example, tool details like name, version, build information, etc., or contact details, phone numbers, email IDs, etc., that may be used for some kind of integration purpose. Well, that's it for this lecture on labels and selectors and annotations. Head over to the coding exercises section and practice working with labels and selectors. In this lecture, we will discuss about the pod to node relationship and how you can restrict what pods are placed on what nodes. The concept of taints and tolerations can be a bit confusing for beginners. So we will try to understand what they are using an analogy of a bug approaching a person. Now, my apologies in advance, but this is the best I could come up with. To prevent the bug from landing on the person, we spray the person with a repellent spray, or a taint as we will call it in this lecture. The bug is intolerant to the smell, so on approaching the person, the taint applied on the person throws the bug off. However, there could be other bugs that are tolerant to this smell, and so the taint doesn't really affect them, and so they end up landing on the person. So there are 2 things that decide if a bug can land on a person. First, the taint on the person, and second, the bug's toleration level to that particular taint. Getting back to Kubernetes, the person is a node and the bugs are pods. Now, taints and tolerations have nothing to do with security or intrusion on the cluster. Taints and tolerations are used to set restrictions on what pods can be scheduled on a node. Let us start with a simple cluster with 3 worker nodes. The nodes are named 1, 2, and 3. We also have a set of pods that are to be deployed on these nodes. Let's call them A, B, C, and D. When the pods are created, Kubernetes scheduler tries to place these pods on the available worker nodes. As of now, there are no restrictions or limitations, and as such, the scheduler places the pods across all of the nodes to balance them out equally. Now let us assume that we have dedicated resources on node 1 for a particular use case or application. So we would like only those pods that belong to this application to be placed on node 1. First, we prevent all pods from being placed on the node by placing a taint on the node. Let's call it blue. By default, pods have no tolerations, which means, unless specified otherwise, none of the pods can tolerate any taint. So in this case, none of the pods can be placed on node 1 as none of them can tolerate the taint blue. This solves half of our requirement. No unwanted pods are going to be placed on this node. The other half is to enable certain pods to be placed on this node. For this, we must specify which pods are tolerant to this particular taint. In our case, we would like to allow only pod D to be placed on this node. So we add a toleration to pod D. Pod D is now tolerant to blue. So when the scheduler tries to place this pod on node 1, it goes through. Node 1 can now only accept pods that can tolerate the taint blue. So with all the taints and tolerations in place, this is how the pods would be scheduled. The scheduler tries to place pod A on node 1, but due to the taint, it is thrown off and it goes to node 2. The scheduler then tries to place pod B on node 1, but again due to the taint, it is thrown off and is placed on node 3, which happens to be the next free node. The scheduler then tries to place pod C to the node 1, it is thrown off again and ends up on node 2. And finally, the scheduler tries to place pod D on node 1. Since the pod is tolerant to node 1, it goes through. So remember, taints are set on nodes and tolerations are set on pods. So how do you do this? Use the kubectl taint nodes command to taint a node. Specify the name of the node to taint followed by the taint itself, which is a key value pair. For example, if you would like to dedicate the node to pods in application blue, then the key value pair would be app equals blue. The taint effect defines what would happen to the pods if they do not tolerate the taint. There are 3 taint effects. No schedule, which means the pods will not be scheduled on the node, which is what we have been discussing. Prefer no schedule, which means the system will try to avoid placing a pod on the node, but that is not guaranteed. And third is no execute, which means that new pods will not be scheduled on the node and existing pods on the node, if any, will be evicted if they do not tolerate the taint. These pods may have been scheduled on the node before the taint was applied to the node. An example command would be to taint node 1 with the key value pair app equals blue and an effect of no schedule. Tolerations are added to pods. To add a toleration to a pod, first pull up the pod definition file. In the specs section of the pod definition file, add a section called tolerations. Move the same values used while creating the taint under this section. The key is app, operator is equal, value is blue, and the effect is no schedule. And remember, all of these values need to be encoded in double quotes. When the pods are now created or updated with the new tolerations, they are either not scheduled on nodes or evicted from the existing nodes, depending on the effect set. Let us try to understand the no execute taint effect in a bit more depth. In this example, we have 3 nodes running some workload. We do not have any taints or tolerations at this point, so they are scheduled this way. We then decided to dedicate node 1 for a special application, and as such, we taint the node with the application name and add a toleration to the pod that belongs to the application, which happens to be pod D in this case. While tainting the node, we set the taint effect to no execute, and as such, once the taint on the node takes effect, it evicts pod C from the node, which simply means that the pod is killed. The pod D continues to run on the node as it has a toleration to the taint blue. Now, going back to our original scenario where we have taints and tolerations configured, remember, taints and tolerations are only meant to restrict nodes from accepting certain pods. In this case, node 1 can only accept pod D, but it does not guarantee that pod D will always be placed on node 1. Since there are no taints or restrictions applied on the other two nodes, pod D may very well be placed on any of the other two nodes. So remember, taints and tolerations does not tell the pod to go to a particular node. Instead, it tells the node to only accept pods with certain tolerations. If your requirement is to restrict a pod to certain nodes, it is achieved through another concept called as node affinity, which we will discuss in the next lecture. Finally, while we are on this topic, let us also take a look at an interesting fact. So far, we have only been referring to the worker nodes, but we also have master nodes in the cluster, which is technically just another node that has all the capabilities of hosting a pod, plus it runs all the management software. Now, I'm not sure if you noticed, the scheduler does not schedule any pods on the master node. Why is that? When the Kubernetes cluster is first set up, a taint is set on the master node automatically that prevents any pods from being scheduled on this node. You can see this as well as modify this behavior if required. However, a best practice is to not deploy application workloads on a master server. To see this taint, run a kubectl describe node command with kubemaster as the node name and look for the taints section. You will see a taint set to not schedule any pods on the master node. Well, that's it for this lecture. Head over to the coding exercises section and practice working with taints and tolerations. Hello and welcome to this lecture. In this lecture, we will talk about node selectors in Kubernetes. Let us start with a simple example. You have a 3-node cluster, of which 2 are smaller nodes with lower hardware resources, and one of them is a larger node configured with higher resources. You have different kinds of workloads running in your cluster. You would like to dedicate the data processing workloads that require higher horsepower to the larger node, as that is the only node that will not run out of resources in case the job demands extra resources. However, in the current default setup, any pods can go to any nodes. So pod C in this case may very well end up on nodes 2 or 3, which is not desired. To solve this, we can set a limitation on the pods so that they only run on particular nodes. There are 2 ways to do this. The first is using node selectors, which is the simple and easier method. For this, we look at the pod definition file we created earlier. This file has a simple definition to create a pod with a data processing image. To limit this pod to run on the larger node, we add a new property called node selector to the specs section and specify the size as large. But wait a minute, where did the size large come from, and how does Kubernetes know which is the large node? The key value pair of size and large are in fact labels assigned to the nodes. The scheduler uses these labels to match and identify the right node to place the pods on. Labels and selectors are a topic we have seen many times throughout this Kubernetes course, such as with services, replica sets, and deployments. To use labels in a node selector like this, you must have first labeled your nodes prior to creating this pod. So let us go back and see how we can label the nodes. To label a node, use the command kubectl label nodes followed by the name of the node and the label in a key value pair format. In this case, it would be kubectl label nodes node 1 followed by the label in a key value format such as size equals large. Now that we have labeled the node, we can get back to creating the pod this time with the node selector set to a size of large. When the pod is now created, it is placed on node 1 as desired. Node selectors served our purpose, but it has limitations. We used a single label and selector to achieve our goal here. But what if our requirement is much more complex? For example, we would like to say something like place the pod on a large or medium node, or something like place the pod on any nodes that are not small. You cannot achieve this using node selectors. For this, node affinity and anti-affinity features were introduced, and we will look at that next. Hello, and welcome to this lecture. In this lecture, we will talk about node affinity feature in Kubernetes. The primary purpose of node affinity feature is to ensure that pods are hosted on particular nodes. In this case, to ensure the large data processing pod ends up on node 1. In the previous lecture, we did this easily using node selectors. We discussed that you cannot provide advanced expressions like or not with node selectors. The node affinity feature provides us with advanced capabilities to limit pod placement on specific nodes. With great power comes great complexity. So the simple node selector specification will now look like this with node affinity, although both does exactly the same thing. Place the pod on the large node. Let us look at it a bit closer. Under spec, you have affinity and then node affinity under that. And then you have a property that looks like a sentence called required during scheduling, ignored during execution. No description needed for that. And then you have the node selector terms, that is an array, and that is where you will specify the key and value pairs. The key value pairs are in the form key, operator, and value, where the operator is in. The in operator ensures that the pod will be placed on a node whose label size has any value in the list of values specified here. In this case, it is just one called large. If you think your pod could be placed on a large or a medium node, you could simply add the value to the list of values like this. You could use the not in operator to say something like size not in small, where node affinity will match the nodes with a size not set to small. We know that we have only set the label size to large and medium nodes. The smaller nodes don't even have the label set, so we don't really have to even check the value of the label. As long as we are sure we don't set a label size to the smaller nodes, using the exists operator will give us the same result. The exists operator will simply check if the label size exists on the nodes, and you don't need the values section for that, as it does not compare the values. There are a number of other operators as well. Check the documentation for specific details. Now, we understand all of this, and we're comfortable with creating a pod with specific affinity rules. When the pods are created, these rules are considered and the pods are placed onto the right nodes. But what if node affinity could not match a node with the given expression? In this case, what if there are no nodes with the label called size? Say we had the labels and the pods are scheduled. What if someone changes the label on the node at a future point in time? Will the pod continue to stay on the node? All of this is answered by the long sentence-like property under node affinity, which happens to be the type of node affinity. The type of node affinity defines the behavior of the scheduler with respect to node affinity and the stages in the life cycle of the pod. There are currently two types of node affinity available: required during scheduling, ignored during execution, and preferred during scheduling, ignored during execution. And there are 2 additional types of node affinity planned as of this recording: required during scheduling, required during execution, and preferred during scheduling, required during execution. We will now break this down to understand further. We will start by looking at the 2 available affinity types. There are 2 states in the life cycle of a pod when considering node affinity: during scheduling and during execution. During scheduling is the state where a pod does not exist and is created for the first time. We have no doubt that when a pod is first created, the affinity rules specified are considered to place the pods on the right nodes. Now, what if the nodes with matching labels are not available? For example, we forgot to label the node as large. That is where the type of node affinity used comes into play. If you select the required type, which is the first one, the scheduler will mandate that the pod be placed on a node with the given affinity rules. If it cannot find one, the pod will not be scheduled. This type will be used in cases where the placement of the pod is crucial. If a matching node does not exist, the pod will not be scheduled. But let's say the pod placement is less important than running the workload itself. In that case, you could set it to preferred, and in cases where a matching node is not found, the scheduler will simply ignore node affinity rules and place the pod on any available node. This is a way of telling the scheduler, hey, try your best to place the pod on matching node, but if you really cannot find one, just place it anywhere. The second part of the property, or the other state, is during execution. During execution is the state where a pod has been running and a change is made in the environment that affects node affinity, such as a change in the label of a node. For example, say an administrator removed the label we set earlier called size equals large from the node. Now what would happen to the pods that are running on the node? As you can see, the 2 types of node affinity available today has this value set to ignored, which means pods will continue to run and any changes in node affinity will not impact them once they are scheduled. The 2 new types expected in the future only have a difference in the during execution phase. A new option called required during execution is introduced, which will evict any pods that are running on nodes that do not meet affinity rules. In the earlier example, a pod running on the large node will be evicted or terminated if the label large is removed from the node. Well, that's it for this lecture. Head over to the coding exercises and practice working with node affinity rules. In the next lecture, we will compare taints and tolerations and node affinity. Hello and welcome to this lecture. Now that we have learned about taints and tolerations and node affinity, let us tie together the 2 concepts through a fun exercise. We have 3 nodes and 3 pods, each in 3 colors: blue, red, and green. The ultimate aim is to place the blue pod in the blue node, the red pod in the red node, and likewise for green. We are sharing the same Kubernetes cluster with other teams, so there are other pods in the cluster as well as other nodes. We do not want any other pod to be placed on our node. Neither do we want our pods to be placed on their nodes. Let us first try to solve this problem using taints and tolerations. We apply a taint to the nodes, marking them with their colors: blue, red, and green. And we then set a toleration on the pods to tolerate the respective colors. When the pods are now created, the nodes ensure they only accept the pods with the right toleration. So the green pod ends up on the green node and the blue pod ends up on the blue node. However, taints and tolerations does not guarantee that the pods will only prefer these nodes. So the red node ends up on one of the other nodes that do not have a taint or toleration set. This is not desired. Let us try to solve the same problem with node affinity. With node affinity, we first label the nodes with their respective colors, blue, red, and green. We then set node selectors on the pods to tie the pods to the nodes. As such, the pods end up on the right nodes. However, that does not guarantee that other pods are not placed on these nodes. In this case, there is a chance that one of the other pods may end up on our nodes. This is not something we desire. As such, a combination of taints and tolerations and node affinity rules can be used together to completely dedicate nodes for specific pods. We first use taints and tolerations to prevent other pods from being placed on our nodes, and then we use node affinity to prevent our pods from being placed on their nodes. Well, that's it for this lecture.
Let's look at resource requirements. Let us start by looking at a 3-node Kubernetes cluster. Each node has a set of CPU and memory resources available. Now, every pod requires a set of resources to run. In this case, for example, this pod requires 2 CPUs and 1 memory unit. Now, whenever a pod is placed on a node, it consumes the resources available on that node. Now, as we have discussed before, it is the Kubernetes scheduler that decides which node a pod goes to. The scheduler takes into consideration the amount of resources required by a pod and those available on the nodes, and identifies the best node to place a pod on. In this case, the scheduler schedules a new pod on node 2 because there are sufficient resources available on that node. If nodes have no sufficient resources available, the scheduler avoids placing the pod on those nodes and instead places the pod on one where sufficient resources are available. And if there is no sufficient resources available on any of the nodes, then the scheduler holds back scheduling the pod, and you will see the pod in a pending state. And if you look at the events using the kubectl describe pod command, you will see there is an insufficient CPU. Now let us now focus on the resource requirements for each pod. So what are these blocks and what are their values? Now you can specify the amount of CPU and memory required for a pod when creating one. For example, it could be 1 CPU and 1 GB of memory. And this is known as the resource request for a container. So the minimum amount of CPU or memory requested by the container. So when the scheduler tries to place the pod on a node, it uses these numbers to identify a node which has sufficient amount of resources available. So to do this in the sample pod definition file, all you need to do is add a section called resources, under which add requests and specify the new values for memory and CPU usage. In this case, I set it to 4 GB of memory and 2 counts of CPU. So when the scheduler gets a request to place this pod, it looks for a node that has this amount of resources available. And when the pod gets placed on a node, the pod gets a guaranteed amount of resources available for it. So what does 1 count of CPU really mean? Now you can specify any value as low as 0.1. So 0.1 CPU can also be expressed as 100M, where M stands for milli, and you can go as low as 1M, but not lower than that. Now 1 count of CPU is equivalent to 1 vCPU. So that's 1 vCPU in AWS. So if you're looking at the AWS cloud, or it could be referred to as 1 core in GCP or Azure, or 1 hyper thread on other systems. And you could request a higher number of CPUs for the container, provided your nodes are sufficiently funded. In this example, I have set it to 5. Now, similarly with memory, you could specify 256 megabyte using the MI suffix, or specify the same value in memory like this. That's the full number, the whole number, and or specify the same value in memory like this as M. So, or use the suffix G for gigabyte. So note the difference between G and GI. So G is gigabyte and it refers to 1,000 megabytes, whereas GI refers to GB byte and that would be equivalent to 1,024 megabytes. So the same applies to megabyte and megabyte and kilobyte and kibibyte. Now let's look at a container running on a node, and by default, a container has no limit to the resources it can consume on a node. So say a container that's part of a pod starts with one CPU on a node. It can go up and consume as much resources as it requires, and that suffocates the native processes on the node or other containers of resources. However, you can set a limit for the resource usage on these pods. For example, if you set a limit of 1 vCPU to the containers, a container will be limited to consume only 1 vCPU from that node. So the same goes with memory. For example, you can set a limit of 512 megabyte on containers like this. Now you can specify the limits under the limits section, under the resources section in your pod definition file. So here, specify the new limits for memory and CPU like this. Now, when the pod is created, Kubernetes sets new limits for the container. And remember that the limits and requests are set for each container within a pod. So if there are multiple containers, then each container can have a request or limit set for its own. So what happens when a pod tries to exceed resources beyond its specified limit? In case of the CPU, the system throttles the CPU so that it does not go beyond the specified limit. A container cannot use more CPU resources than its limit. However, this is not the case with memory. A container can use more memory resources than its limit. So if a pod tries to consume more memory than its limit constantly, the pod will be terminated, and you'll see that the pod terminated with an OOM error in the logs or in the output of the describe command when you run it. So that's what is OOM refers to, out of memory kill. So now that we have learned what resource requests are and what limits are and how they function and what happens when a particular container or pod hits the limits of that were defined, let's see what the default configuration is, right? So by default, Kubernetes does not have a CPU or memory request or limit set. So this means that any pod can consume as much resources as required on any node and suffocate other pods or processes that are running on the node of resources. So this is very, very important to note. So let's just look at how CPU requests and limits work. Let's say there are two pods competing for CPU resources on the cluster. And when I say pod, I mean a container within a pod, right? So just keep that in mind. So without a resource or limit set, one pod can consume all the CPU resources on the node and prevent the second pod of required resources. So of course, this is not ideal. Now let's look at another case where we have no requests specified, but we do have limits specified. In this case, Kubernetes automatically sets requests to the same as limits. For example, requests and limits are assumed to be 3 in this case, and each pod is guaranteed 3 vCPUs and no more than that, as limits are also set to the same. The next one is where requests and limits are set. In this case, each pod gets a guaranteed number of CPU requests, which is 1 vCPU, and can go up to the limits that is defined, which is 3 vCPU, but not more. So this might look to be the most ideal scenario. However, the issue is that if pod 1 needs more CPU cycles for some reason, and pod 2 isn't really consuming that many CPU cycles, then we don't want to limit pod 1 of CPU, right? So we'd like to allow pod 1 to use the available CPU cycles as long as pod 2 doesn't really need it. So if there are sufficient CPU cycles available on the system, then why not let the pods use them, right? So we don't want to unnecessarily limit resources of CPU cycles. So that is not really the ideal scenario. And that's where the last scenario comes in. So setting requests but no limits. In this case, because requests are set, each pod is guaranteed 1 vCPU. However, because limits are not set, when available, any pod can consume as many CPU cycles as available. But at any point in time, if pod 2 is requires additional CPU cycles or whatever it is it has requested, then it will be guaranteed its requested CPU cycles. So this is the most ideal setup. Of course, there are cases where you absolutely may want to limit a pod of resources, and in that case, you may set limits. For example, a good use case for setting limits is our labs themselves, where all the labs that you guys have been going through and accessing as part of this course, they are hosted as containers on a cluster, right? And since it's made accessible to public and users can run any kind of workload that they want, we set limits to prevent a user from misusing the infrastructure to, let's say, perform Bitcoin mining or other resource consuming activities. So that works for us in that case. But in your case, if you don't want to restrict your application to consume additional CPU, if needed, then you could consider not setting limits. But remember, if you were to do that, you need to make sure that all the pods have some requests set, because that's the only way a pod will have resources guaranteed when there are no limits set for other pods, right? So if there is any pod that has no requests set, and there are no limits set for all the other pods, then it's possible that any pod could consume all of the memory, all of the CPU that's available on the node and starve the pod that has no request defined. So just make sure that you'll have to set requests for all the nodes. So a couple of things to note: the requests and limits may be different for each pod, but for the sake of simplicity, we are assuming that it's the same for both pods in these examples that I'm sharing here, right? But you can have absolutely different requests or limits set for containers, for each containers within each pod. So also note that these recommendations are just for CPU. So let's look at how it works for memory next. So it's kind of similar. So if you look at the memory, let's say there are two, in the first case, there are two pods competing for memory resources on the cluster, and without a resource or limit set, one pod can consume all the memory resources on the node and prevent the second pod of required resources. So this is not ideal. Now let's look at the case where we have no requests specified, but we do have limits specified, and in this case Kubernetes automatically sets requests to the same as limits. So for example, requests and limits are assumed to be 3 GB bytes in this case, and each pod is guaranteed 3 GB bytes and no more, as limits is also the same. The next one is where requests and limits are set. In this case, each pod gets a guaranteed amount of memory, which is 1 GB byte, and can go up to the limits defined, which is 3 GB bytes but not more. And the last one is setting requests but no limits. In this case, because requests are set, each pod is guaranteed 1 GB byte. However, because limits are not set, now when available, any pod can consume as much memory as available. And if pod 2 requests more memory to free up pod 1, the only option available is to kill it. Because unlike CPU, we cannot throttle memory. Once memory is assigned to a pod, the only way to kind of retrieve it is to kill the pod and free up all the memory that are used by it. Okay, so now, as we discussed before, by default, Kubernetes does not have resource request or limits configured for pods. But then how do we ensure that every pod created has some defaults set? Now, this is possible with limit ranges. So limit ranges can help you define default values to be set for containers in pods that are created without a request or limit specified in the pod definition files. This is applicable at the namespace level, so remember that. And this is an object, so you create a definition file with the API version set to v1, kind set to limit range, and we'll give it a name, CPU resource constraint. We then set the default limit to 500M, default request to the same as well. We will also specify a max CPU as 1 and a minimum as 100M. So the max refers to the maximum limit that can be set on a container in a pod, and minimum refers to the minimum request a container in a pod can make. So these are, of course, some example values, not a recommendation or anything. So you must set whatever is best for your applications. So the same goes for memory. Use memory instead of CPU and specify the defaults and max and min values in this form. Note that these limits are enforced when a pod is created. So if you create or change a limit range, it does not affect existing pods. It will only affect newer pods that are created after the limit range is created or updated. And finally, is there any way to restrict the total amount of resources that can be consumed by applications deployed in a Kubernetes cluster? For example, if we had to say that all the pods together shouldn't consume more than this much of CPU or memory, what we could do is create quotas at a namespace level. So a resource quota is a namespace level object that can be created to set hard limits for requests and limits. In this example, this resource quota limits the total requested CPU in the current namespace to 4 and memory to 4 GB byte. And it defines a maximum limit of CPU consumed by all the pods together to be 10 and memory to be 10 GB byte as well, right? So that's another option that can be explored. Well, that's all for now. Refer to these pages on the Kubernetes documentation site for more information, and head over to the labs, and I'll see you in the next one.